Students, are you able to see the PPT?
Yes, sir.
Okay, so in the revision class, you attend these classes seriously. We will cover the important questions and we will revise the things also, right? So all these things, whatever we discuss, all the important things, if you look towards your end semester examination or mid semester examinations, even for other things. How many students are there? 35. Okay, so I will start with the unit 4 hybrid pi model, and here one important question can be from this hybrid pi model is calculation of short circuit current gain, right? So you have to find out the expression for the short circuit current gain, or you have to draw the diagram of hybrid pi model, right? So in this case, we just quickly refresh the things. See here, this is our transistor, and inside the transistor there is one point, right? This. Okay, so this point we call it as B dash, right? So this is virtual point. B dash is virtual point. It cannot be accessed by the user. We cannot access this, right? But internally you can find that, see, this is the B terminal. B terminal we will connect from here. C terminal we will connect from here. And E we will connect from here. So right, so metal lead we will connect, and user can use these terminals. But internally there is one point called as B dash, which is virtual point. Okay, so a resistance is there. You can find the resistance between B dash and B, and this resistance is represented as RBB dash, right? This is RBB dash, and there is a resistance between this virtual point B and this emitter. So this is REB dash between emitter and B dash virtual point. Same way there is a internal resistance is formed RCB dash. So this is formed between the collector terminal and virtual point. Okay. So now, so this B dash RBB dash is also called as base spreading resistance, right? So now, if we draw the hybrid pi model, then it looks like this. See, emitter is common. We are drawing the hybrid pi model of a common emitter transistor, right? Only this is in the syllabus, common emitter transistor hybrid pi model. So common emitter transistor, it looks like this, right? So here this is emitter terminal. This is your emitter terminal, right? And here this is our base, and here we are having this collector. So at this is the input section, and this side is your output. So emitter is common. That's why you see here I've drawn one common line. This emitter, this is common. Okay. Now you come to the base side, input side. So in input we are having this base terminal. Then there is a resistance, internal resistance, base spreading resistance, which is formed between the base terminal and the virtual point B dash, and this RBB dash. So this resistance represents your base spreading resistance. Okay, and this is your internal point. You can see this transistor here, right? So this emitter, okay, in this way you visualize. So this is my input section. So here B terminal and this resistance RBB dash, this resistance is there between B terminal and B dash terminal, right? And from B dash terminal to emitter there is a resistance REB dash, and between B dash to C there is a resistance RCB dash. So same way we have drawn this, right? You can see this. So this is the resistance RBB dash between B and B dash. Okay. Then between B dash and E, there is resistance, internal resistance RB dash E. Okay. This resistance will be there. Now these resistances I have also expressed in terms of conductance. So here GBB dash is equal to 1 by conductance is 1 by resistance. So it is 1 by RBB dash. Same way GB dash E will be represented by 1 by RB dash E. This, okay, right. And here you can find a voltage drop between this voltage terminal B and E. The voltage measured is voltage between base and emitter. Same way, if here between B dash and E, I have written the voltage B dash E. Okay, so the voltage which we are representing between virtual point B dash and emitter is VB dash E. Right. Now here we come to this B dash terminal. So now already we know that since, see, this is a transistor, right? This is a transistor like N, P, N, and we know that at the junction due to the depletion layer, one capacitance will also form. So this is my CE capacitor, and same way you will find a capacitance which is formed between collector and base terminal, right? Here also you will find one capacitor, right? These capacitances we neglect when we operate our transistor in low frequency region, but in higher frequency region we have to consider these capacitances. So you see here between virtual point B dash and emitter, you find one capacitor here, C E dash, right? So this capacitance is formed between base and emitter, right? Now between virtual point B dash and this C, you can find another capacitor CC. This capacitor is internal capacitor which is formed between the collector and base terminal, right? And here you can find this resistance RB dash C, right, between virtual point B dash and the collector terminal. Okay, right. So now here RB dash C and CC, these are our feedback element, right? Because these resistances and capacitances are connected between our collector terminal, which is a output terminal, and between our B dash terminal, which is at the input side. So these are also called as feedback element. Now at the output side, you can find voltage VCE, voltage between collector and emitter, right? So this voltage is mentioned here with positive terminals at collector side, negative at emitter side. Then now you can see here, suppose this is your transistor N, P, N, right? This is collector, base, emitter. So current is basically flowing in this way, right? Current is flowing in this way from collector to emitter. So one resistance will be there. You can find one resistance when current will flow through these materials NPN. Then you will find one resistance between this collector and emitter. So this I am representing here. RCE, resistance between collector and emitter. Okay, and it is represented in terms of conductance GCE is equal to 1 by RCE. And here there is one current source, and current source means if you write the expression for current, so it will be V by R, right? Or you can write it V multiplied by 1 by R, or V multiplied by 1 by R is your conductance, right? It is your conductance. So this current source is represented by Gm multiplied by Vb dash E. So this is a dependent current source, and its value depends upon the voltage at the input side, that is Vb dash E. Okay, right. And Gm is the conductance. Okay, right. So now with this, so this is a hybrid pi model. Sometimes question can be asked like 2 marks question, 3 marks question, simply draw the hybrid pi model. So you should be able to draw this hybrid pi model, and you label various terminals, various resistances. Okay, in this way. Now another question can be the common emitter short circuit current gain. This you have to derive. So for this derivation, you require hybrid pi model. Okay. So this is my hybrid pi model. I have again redrawn the same thing here in figure number 1. Only thing is here you can find I included this resistance, load resistance RL. Okay. And across RL, I am measuring a voltage, and that is the voltage between collector and emitter. And same voltage you can find here. So whether you measure the voltage from this side or this side, across this RL you will find the same voltage. So here also you will find VCE. Okay. Now if you come to the input side, so this is base terminal B. This is our emitter, which is common. So here also it is emitter. Emitter. This is common. Now input current is IB, right? That is your base current. Now RBB dash, this is a base spreading resistance. Already we have seen in previous slide. And here this is the resistance between base, virtual base terminal and emitter. So VB dash, this RB dash E, this resistance. So voltage across this RB dash E is VB dash E. This CE is a capacitance which is formed between base and emitter. Cc is the capacitance which is formed between virtual terminal B dash and collector, and RB dash C is the uh, resistance formed between virtual point and collector. Okay, so it is the same figure, only thing I added here RL, right? So now here you can see this RB dash C and CC, they are acting as a feedback element, right? So we have to use the Miller theorem to simplify this circuit. Now, as per the Miller theorem, you can see here, if you have this type of circuit, right, where there are the ports 1 and 1 dash, there is another port 2 and 2 dash, and this is some 2-port network, right? And this is one point A, which is at input side, another point B at the output side. And in between these input and output point, we have connected one impedance Z. Okay, so one impedance Z is connected between input and output connections, right? So Z again here is a feedback element. So this Z can be splitted in two parts, because due to presence of this Z, which is connected to input and output section, the calculation is difficult. So we will use the Miller theorem, and in Miller theorem, what will be done? This Z will be removed from here, and one impedance Z1 will be connected at the input side. Okay, and another impedance Z2 is connected at the output side. So here the feedback impedance, this Z is removed, and it is split in two parts. One is Z1 and another is Z2. Okay, so Z1 at input side and Z2 at output side. Okay, right. So now what will be the value of Z1 and what will be the value of Z2? So uh, Z1, if this Z impedance is resistive, then you can find its value as Z by 1 minus AV, where AV is the voltage gain. Okay, and suppose if Z in place of resistance, it is a capacitance you have connected here, then in place of Z1 I will use the value C1. Okay, so C1 will be connected here. If this Z is a capacitor, then its value will be whatever is the value of capacitor C multiplied by 1 minus voltage gain. Okay, now same way at the output side, if this Z is resistive in nature, then this Z2 will be expressed by this expression, Z by 1 minus AB var, AB inverse, right? This is voltage gain inverse. So see the difference. In Z1, we will take the voltage gain, and in Z2, we will take the inverse of the voltage gain. Only this difference is there. And if this Z is a capacitive, then at the output side, you have to connect one capacitor, C2. Its value will be C into 1 minus AB inverse, just like this, right? Only thing is, difference is in place of this AB, you have to use AB inverse. Okay, so now if you see here in this particular circuit diagram, hybrid pipe model, this RB dash C. So this is a feedback element. So this will be splitted by using Miller's theorem. And since this is a resistance, so the formula used will be this formula. This, okay, for the input side, and this will be used for the output side. And for this CC, again this CC will be splitted, and for CC we will use this formula to connect the capacitor at the input side, and to connect the capacitor at the output side, this formula. Okay. So with this background, now we will move further. So now you can see this diagram. So in this diagram there is no change. Already RBB dash was there. Okay. RB dash E was there. You can see here. RBB dash, RB dash E, and this CE. These three things are already there. So you can find in this diagram also these three things. This RBB dash, RB dash E, and this CE. It is there. Now what I have done, this RB dash C, this I have connected at the input side by using Miller theorem. And in Miller theorem, we will use this formula. According to this formula, this I will connect here this resistance, right? And its value is R B dash C by 1 minus voltage gain. 1 minus voltage gain, right? And for the capacitor, we are having capacitor CC into 1 minus AV. Okay. So in this way, at the input side, this CC and this RB dash C will be represented by using Miller's theorem. So you can find here this RB dash 1 minus voltage gain. Then C 1 minus AB, this. Okay. Now you come to the output side. In output side, already this current source is already there, right? GMVB dash E. Now this RL is already there. This RCE is already there. Now only we have added one this resistance and one this capacitance by using Miller's theorem. So what is the formula? If we are having resistance, then we will use this formula, right? So what value we have written for this resistance? RB dash C, right? RB dash C is the component, this one, RB dash C, divide by, see here, divide by 1 minus AB inverse. So AV inverse, this we can write as 1 by AV, right? Both are same. So I have written this 1 minus 1 by AV, right? Same way for the capacitor also I have written this value for this capacitor by using Miller's. So this value I got from this expression, right? So CC is equal to so value of this capacitor is CC multiplied by 1 minus AB inverse. So this is CC multiplied by 1 minus AB inverse, right? So these values we have written. Okay, simply we have applied the Miller's theorem. Okay, so after Miller's theorem, this figure we are having, right? So this is a figure after applying Miller's theorem on the feedback component of figure 1. Now we have to find the short circuit current gain, right? Short circuit means what we will do? We will short circuit here. We will short circuit here, right? So if RL is short circuited, the voltage across RL is 0. So if you find any short circuit here, then voltage across RL will be 0. So this VCE, this will be 0. Okay. Now what is the voltage gain? Voltage gain is output voltage by input voltage. So output voltage is VCE and input voltage you have to consider here. VB dash E. This one. You don't consider this. This is the overall voltage gain, right? Overall voltage gain means extremely output and extremely input you should take. But here we are talking about this voltage gain where the output voltage is VCE and input voltage we are taking from this virtual point VB dash E. So voltage gain is VCE by VB dash E, and VCE due to this short circuit is 0. So our voltage gain is 0, right? So voltage gain is 0 now. Now another thing, due to short circuit, all the components connected in the parallel to a short circuit will also become short circuit, because if you think, you just see, if you are having this one resistor, this second resistor, this some third resistor, okay, and here you have connected some voltage source like this, okay. So now what will happen? Current, it will flow in this resistor, it will go in this resistor, it will go in this resistor, everywhere it will go. But if you short circuit this, then what will happen? Then all the current will pass through this short circuit path. It will pass through this short circuit path. So current will not go in these parallel components, which are resistors. So once you make the short circuit, then all the components in the parallel path will be short circuited, right? So in the output side, so in output circuit, RCE, this will be short circuited. Then this capacitor, this will be short circuited. Then this resistance, this is also short circuit, okay. But this voltage dependent current source, this will not short circuit, because here this will depend upon the voltage VB dash E, which is at the input side, here, VB dash E. This voltage is at the input side, so this current source depend upon a voltage which is at the input side, so this will not short circuit. Otherwise all these three components will be short circuit, okay. So if they will short circuit, then how the circuit will look, you see, okay, that we will draw the circuit diagram afterward. But another, now we will see at the input side. At the input side, since AV is 0, already we have seen that due to the short circuit, AV will become 0. If AV will become 0, then in the input side, you see this expression. Here AV is 0. So this expression will become RB dash C. Now see this expression, CC into 1 minus AB. AB is 0, so this expression will also become CC. So now you see the circuit diagram, how it looks. At the output side, there is this current source and one current I short circuit current is there, okay, due to short circuit which we made. And at the input side, you can see this CC, this RB dash C, because AV component is 0. So due to that, this will become RB dash C, this will become CC. So those things you are seeing here, right? And this capacitor is already there, this RB dash E is already there, and RB dash is there, right? So from this circuit diagram, this will become RB dash C, this will become CC, right? And this is already there, this is already there, this is already there. This is IB, this is B terminal, this is E terminal, here it is B dash terminal, this is RB dash E. So now you can see the circuit, it looks like this, right? Circuit looks like this. Now if you see, if from this point, if you look inside your this circuit, right, you look inside from this circuit, then you find that capacitances and resistances, they are connected in parallel, right? So what we will do, if we are seeing equivalent resistance from a point, so from this point, if you are seeing the resistances, then ignore the capacitance. So if I will ignore the capacitance, I will ignore this capacitance and I will ignore this capacitance. So from here, if I will look, then R in, then resistance, input resistance here is this resistance RB dash E. It is in parallel with RB dash C. So same thing I have written. Right? R in is equal to RB dash E parallel to RB dash C. Okay. And if we are seeing the equivalent capacitance, now if you are seeing equivalent capacitance, then we will neglect the resistances. So if you neglect the resistance, then this resistance, everything will be removed, and only you will find CE capacitance is in parallel with CC capacitance, right? This CE capacitance is internal capacitance formed between base and emitter. CC is internal capacitance formed between base and collector. So only these two capacitors are in parallel. So parallel capacitors, the equivalent capacitor, if you want to calculate, then you have to add those. So simply equivalent capacitance will be CE plus CC. Okay. And Rin, if you see the Rin, then Rin is RB dash E parallel with RB dash C. Okay. Now you just see, if you recall our NPN transistor, right? This is our NPN transistor, emitter, base, collector, right? So between base, this is one point B dash, virtual point. So here you will find one resistance, right? Okay, I will draw properly. Okay, I will use this figure itself. Okay, see this figure. See, emitter, if you recall the doping level of emitter, if you compare the doping of emitter and collector, then emitter is heavily doped. Highest doping is there. Heavily doped. And collector is medium doping. Base is lightly. So if there are more heavily doped, means there are more number of charge carriers. Charge carriers, right? In emitter, NPN, charge carriers are electron, and in collector the charge carriers are electron, but their number is less as compared to the emitter. So you see, in emitter, if the charge carriers are more, then its resistance will be less, right? Because charge carrier contribute the current conduction. If more current conduction carriers are there, then its resistance will be less. So you will find that REB dash is less. And what about this RCB dash? So this resistance is more, right? Because charge carriers are less. So in this way, the resistance of this REB dash, it will be around 1 kilo ohm, and for this it will be around 4000 kilo ohm, right? So this 4000 kilo ohm can also be written as 4 mega ohm, right? So REB dash is much smaller than RCB dash, right? So if there are two resistances, are in parallel, one is of 1K, another is of 4K, then the equivalent value of the resistance will be near to this 1K, right? Then equivalent, if you calculate this R total, then it will be near to this 1K, correct? Because 1K multiplied by 4 K divided by 4 plus 1, 1K plus 4K. If you solve this, then you find that it is near to this 1K. Okay. So now same concept you can see here. Yes. So you see this Rn is Rb dash E parallel with Rb dash C. So Rb dash E is in the range of 1K. Rb dash C is in the range of 4000 K. Right? I'm talking about high frequency, at high frequency range. Right? Because we are modeling at the high frequency. For the high frequency modeling, we require pi model. For the low frequency modeling, we require hybrid parameter, H parameter model. So here the input resistance, this, it will be around 1 kilo ohm, right? It or R B dash E. So we will neglect this R B dash C part. We will neglect this because it is in parallel with R B dash E, right? And R B dash E value is much lower. So overall value will be much lower. Okay. Right. So now the circuitry will look like this. Okay. See here, this resistance and this resistance. In these two resistances, what we have done, we have neglected this one, right? So now you see the new figure here. RBB dash is already there, RB dash E is there, and CE and CC is there. Okay, and one RB dash C I have removed, right? Because we have neglected that. Now in the output side, you can see this I short circuit, this current is equal to minus GM V B dash E, right? So both the current will be same. Short circuit current is equivalent to this voltage dependent current. Only thing is that direction is different. That's why I kept the minus sign, right? And we will write this expression as expression number 1. Okay. Now you see the input side. In input side B, here we are having one current IB and RBB dash, IB and RBB dash, and this portion. This portion, I am representing this portion by Z in. Okay. So basically, if you see this Z in, how it looks like this. There is one resistance RB dash E. Then here we have two capacitances in parallel. One is CE, another is CC. So you see this part, right? It looks like this. Okay, Zin is looking like this. Okay. So now Zin, how we represent this Zin? Zin can be represented by, right? This R B dash E multiplied by this part, divide by R B dash E plus this part, right? So if you want to represent this, see how it is represented now. See this. R B dash E multiplied by this capacitive part. So equivalent capacitance is, there are two parallel capacitances. So equivalent will be CE plus CC. This, right? And into 2 pi by 1. See how we represent this capacitive reactance. If you recall, capacitive reactance we represent by 1 by 2 pi f c. By this only we represent. So you see here 1 by 2 pi f and C means equivalent capacitance. CE and CC, they are in parallel. So we have written at CE plus CC. Okay. So and 2 pi f can be written as omega. So you see same way I have written here 1 divided by omega CE plus CC and imaginary part we have written as G. Right. So in this way we have represented this parallel capacitor. Right, and in the denominator RB dash E plus this part, capacitor part, reactance. Okay, so this is equivalent to your Zin. So Zin is represented by this way. Okay, so same thing is written here. So now if many things are in parallel, then the impedance become complex. So in place of impedance we write admittance. So here you can see here. Now many things are in parallel. This all are these are in parallel. So if many things are in parallel, then in place of impedance, it is better to use the admittance for the calculation. So only thing is what I have done. Uh, so this is your Y in admittance is equal to 1 by Z in, and this is equal to so this part, right? This part what I have done, you can see here 1 by Z in. 1 by Z in means I will write it as R B dash E plus 1 by, because this will go in the numerator, 1 by J omega C E plus C C. Okay, and divide by R B dash E 1 by J omega CE plus CC. This. Okay. So first what we have done, we have taken this part. So what we will get for this, R B dash E and R B dash E will be cancelled out, and we will get 1 by 1 by 1 by J omega CE plus CC. So you see this part we will get. Okay, right. And then now for the second part, what we have done, you consider only this part. Right. Then what we will get, this and this will be cancelled out, and we will get 1 by R B dash E. So you are getting this R B dash E. Okay. So R B dash E in terms of conductance we can write G B dash E, right? And here this we will take at the numerator side, so you will get plus J omega CE plus CC. Okay, and here Y in is admittance. So this we will get expression. So now you can see the figure is like this. This is IB, RB dash, RBB dash. This is admittance, and this IB same current is flowing through the admittance, and across this admittance we are, this is the voltage VB dash E, right? Which is VB dash E is the voltage across the admittance YE. So VB dash E is equal to IB into Z in, right? So here if you write Z, so multiply it by IB, so that will be your this voltage, same I have written here. So, and Z in you can write it as 1 by Y in. So I have written this expression now. Now in this expression, in the both side, right? In the both side, I will multiply it by Gm. So I will get Gm VB dash E, and towards right side, I will get Gm multiplied by this IB by Y in, IB by Y in. Okay, this I will get. Now already see, already I know this expression 1 is ISC by this. So now from 1, if I this then or I minus ISC minus short circuit current is equal to GM V B dash E, right? So here you can see ISC minus ISC is equal to GM, right? And VB dash E. VB dash E, from here you can find it. If you cancel out GM, or directly from here also you can get IB by Y in. So IB by Y in multiplied by GM, right? So from this expression itself. Now ISC by IB. IB I will bring towards left side. So ISC by IB. This will be equal to this minus GM by Y in. And this ISC by IB is your short circuit current gain, right? Output current is ISC, short circuit current. And input side it is IB. This is your input side. If you recall, here we short circuited this section, right? So this current, your ISC. So its current gain is short circuit current gain is minus GM by YN. Okay. Okay, so up to here we have done. So then this short circuit current gain is can be written as minus GMY. Now in place of Y in, what I have done, I have written the expression of Y in, which this expression, right? Y in is equal to G B dash E plus J omega C E plus CC. So this only I have written G B dash E plus J omega C E plus CC. Now in numerator and denominator, I will divide by G B dash E. Right, this term G B dash E, this I will divide in numerator and denominator. So what I will get in numerator, GM divided by G B dash E. In denominator, this part will become 1, and here J omega CC plus CE divided by GB dash E. Okay. So again, this in this part, what I have done in this expression, what I have done, this GB dash E. So this I have written in terms of resistance, right? So 1 by GB dash E can be written as RB dash E. Okay. So up to here there is no problem. Now you see this numerator part, this GM by GB dash E, it is equal to HFE, right? HFE value in the transistor, in standard value of HFE is 50, right? So the ratio of this GM and VB dash E is 50. So you can write this GM by GB dash E as HFE also, right? So here I have given those values also. GM is standard value of GM is 50 milliampere per volt, and GB dash E is 1 milliampere per volt. These are the standard values. So GMY GB dash E will be 50, and this 50 is equivalent to this HFE. Standard value of HFE is 50. That's why GMY GB dash E I am representing as minus HFE by HFE. Okay. So now short circuit current gain expression. If it is asked in the examination, then you can calculate up to this point. You calculate up to this point, right? Further simplification is also there, and that will be in other terms. So for example, you can see here this expression, this expression, how I have written current gain, short circuit current gain is equal to minus HFE divided by 1 plus j omega R in plus R in Ci. So what is R in? If you recall, R in, it was R B dash E in parallel to R B dash C, and since the value of R B dash E was very less, that's why we neglected R B dash C, right? So this R B dash E, you can write it as IR in, and this CE plus CC, this we can write it as CI input, right? So same expression I have written here, this one. And now next step you see AISC is equal to minus HFE in the numerator, denominator 1 plus, now J in place of omega I have written 2 pi f, this, right? And divide by R in Ci, how I have written, divide by 1 by R in Ci. In this way I have written this, right? There is one purpose why I am doing this, right? And after this you come to the in this expression. Now numerator, there is no change in the numerator, 1 plus in denominator 1 plus j, then this 2f, this also I brought to the here denominator side. So here it will become 2 pi ri ci, and in the numerator we have only f, right? So now this whole portion 1 by 2 pi ri ci is represented by f beta, and this is called as upper 3 dB frequency, right? F beta is upper 3 dB frequency, and its expression is 1 by 2 pi ri ci, where ri is rb dash e and ci is ce, and internal capacitance which are formed between base and emitter and base and collector. So if in examination question is asked to calculate the value of upper 3 dB frequency, then you can calculate if these values are given. You can calculate by that way also. Okay. So F beta is also called as common emitter short circuit current gain cutoff frequency, right? And now you see the current gain expression. It is equal to minus HFE in the numerator, and in denominator 1 plus J F by F beta, this term, right? This term has come. Okay, so I stop here and I will continue from here to next class, right? So this is important. You recall these things and I explain these things properly. These video also I am recording. You can get these videos also through the Teams, and from examination point of view also these are important even for end semester, right? Because if some question is framed in this hybrid pi model, then obviously this question will come, right? Okay, so I stop here now.